In today's video, we're back with Rami RC, who absolutely surprised us with a heavy-duty jet aircraft project. He built a remote-controlled scale version of the Pilatus PC-24 with an impressive wingspan of nearly 6 meters and a final weight after painting that reached 86 kilograms. This is a massive project by every possible standard, one of the most ambitious and impressive builds he has ever worked on in the history of his channel. But before we jump in, make sure to support us by hitting the like button and subscribing, so we can continue bringing you high-quality content like this. Thank you all for the incredible support we keep seeing. Now, without further delay, let's get started. What really makes this project special is that every single detail of this aircraft was designed based on real aviation principles. From the very first design stage all the way to final flight readiness, every step was carefully planned and precisely executed. The process started with manufacturing custom molds for the fuselage. Instead of carving the body from a single solid block, CNC machines were used to shape the molds with extreme accuracy. The molds were then coated with a special protective release layer, followed by multiple layers of carbon fiber. Everything was compressed using vacuum infusion technology to eliminate excess resin and keep the weight as low as possible in critical areas. A honeycomb core was added to reinforce the structure without adding unnecessary weight. The fuselage itself was built in 2 main sections, which were later bonded together using specialized aerospace-grade adhesive and reinforced with carbon fiber tape to increase overall rigidity. The design features straight wings, specifically chosen to reduce takeoff and landing distances, while also providing excellent stability at low speeds. At the same time, the wings are engineered to be lightweight yet extremely strong. The wing core was manufactured from compressed foam using CNC machines, giving it the exact aerodynamic profile required, while significantly reducing weight. To strengthen the wings and evenly distribute loads, carbon fiber spars were used, along with internal honeycomb reinforcements. Since the fuselage is the central structure that carries nearly all major loads, it had to be lightweight but also exceptionally strong and durable. It houses critical components such as the landing gear, wing mounting points, engine mounts, and control linkages. The main structure was built in multiple stages, with each section manufactured separately to simplify transportation and final assembly. Once all parts were cured, they were assembled with extreme precision to maintain proper balance across the entire aircraft. Next, we move to one of the most important components for stability and control, the horizontal stabilizer. This part plays a major role in controlling pitch, allowing the aircraft to climb or descend smoothly. It had to be designed using lightweight materials that could still withstand aerodynamic loads during flight. This component was made from reinforced foam layered with carbon fiber, ensuring structural stability even under intense airflow pressure. Most of the aircraft components were made from carbon fiber, which is known for being incredibly lightweight while offering exceptional strength. This allows the aircraft to fly faster and operate more efficiently. In high-stress areas such as wing supports and main structural joints, carbon fiber served as the primary load-bearing material. This also resulted in a smooth, clean exterior surface, significantly reducing aerodynamic drag. All components were wrapped in multiple layers, creating a strong outer shell that minimizes airflow disturbances over the aircraft body. Now we reach one of the most sensitive areas of the build, the engine nacelles. Since the original aircraft operates with twin-jet engines, the nacelle design had to be extremely precise, accurately replicating real aircraft engine installation while ensuring efficient airflow with minimal resistance. Carbon fiber reinforcement rings and structural supports were added around the engine mounting areas to withstand high air pressure during flight. The internal engine ducts were manufactured using CNC machines for maximum accuracy and assembled using specialized aviation-grade adhesives. The internal thrust channel was carefully designed to guide airflow smoothly from the EDF units all the way to the exhaust outlet. As you can clearly see, wings are the core of any aircraft. They generate lift, maintain flight, and allow the aircraft to maneuver left and right by controlling airflow around the wing. This works by creating a pressure difference between the upper and lower wing surfaces. The aerodynamic shape causes air to move faster over the top of the wing and slower underneath, resulting in lower pressure above and higher pressure below. This pressure difference generates lift and allows the aircraft to rise and remain airborne. The first step in wing construction was shaping the core from lightweight yet strong foam, specifically compressed polystyrene. This foam acts as a lightweight internal structure, providing volume without adding unnecessary weight. For precision, CNC machines were used to cut channels and cavities for wiring and internal components. After that, the main spars were installed using extremely strong adhesive, followed by additional wooden reinforcements to distribute loads more evenly throughout the wing. This internal structure closely mirrors real aircraft construction, which relies on composite materials and reinforced metals to withstand flight stresses. Once the structural work was complete, electrical wiring and servo bays were installed inside the wings. Lighting connection points were added, along with the retractable landing gear mechanisms. The servos receive commands from the wireless transmitter and convert them into smooth, precise movements. Installation had to be extremely accurate to ensure correct angles and prevent unnecessary drag or instability. When it comes to the retractable landing gear system, this is far more than a simple mechanical motion. The system operates using electronic motors controlled by specialized control units, which determine exactly when the landing gear deploys or retracts during takeoff and landing. This model accurately replicates the retractable landing gear design of the original aircraft, significantly reducing aerodynamic drag while in flight. Proper electronic wiring between all components was absolutely critical. High-quality insulated cables were used to ensure clean signal transmission without interference. Power distribution was carefully managed using ESC units and central control modules, which regulate voltage levels and prevent sudden spikes that could damage servos or motors. Cable selection was done based on electrical resistance, insulation quality, and flexibility, since poorly designed wiring would not withstand vibration and movement during flight. At this stage, electromagnetic shielding becomes essential. Cable routing was carefully reviewed, especially near powerful motors that generate strong electromagnetic fields. These fields could disrupt signal transmission or even cause complete loss of control during flight. To prevent this, twisted pair wiring was used along with ferrite beads to suppress unwanted electrical noise. Cables were routed through designated paths inside the fuselage and wings, away from heat sources and interference points. In areas near high-temperature components such as ESC units, heat-resistant thermal shielding was applied to protect the wiring. Once everything was completed, ground testing began on all mechanical and electrical systems to ensure flawless operation. After confirming that all technical parameters met specifications, the aircraft was prepared for painting. Painting here wasn't just for aesthetics, but also to protect the surface, improve aerodynamic smoothness, and make the aircraft easier to track visually while in flight. And now, the aircraft is ready for takeoff. This machine is not just a scale model. It was built with precision, patience, and an endless drive for excellence. Every strand of carbon fiber represents Rami's dream, reigniting passion, courage, and the relentless desire to push limits and fly farther and farther. And with that, we've reached the end of the video. If you enjoyed it, don't forget to like, subscribe, and share. I'll see you in many more videos.